Alright, so in this video we'll be dealing with the Unit 9 material. So this was our unit on light and electron configurations and electronic structure and those things. So if you look at the top, you'll see here are all of the eligible topics we talked about. So I would suggest make sure you know what all those mean and that you can sort of check off all those boxes. But we start off with a bunch of definitions. So these are things that you can look up in your notes yourself, but I'll give you quick overviews. Okay, so the difference between the ground state and the excited state for an atom: the ground state is where all the electrons are in their lowest energy levels. The excited state is where you have one or more electrons in some energy level above their normal state. So essentially they're in higher energy levels compared to their regular ones. Okay, electrons that are in the ground state only stay there temporarily. Eventually they will fall back down to the ground state. When they do that, when they fall from the excited state to the ground state, they do emit energy, which we would see as a photon of light, depending on its wavelength and frequency. Okay? Question 2, it asks about the 3 rules that sort of dictate how electrons fill into an atom. Right? So again, look up the definitions in your Unit 9 notes. If you don't have them, they're all still on Schoology. But the Aufbau principle is essentially the idea that electrons always fill from the lowest to highest energy levels. The Pauli exclusion principle is the idea that electrons in orbitals have opposite spins. So how that affects you when you are drawing orbital diagrams, you always drew the first arrow up and the second arrow down in a box. And then our last one, Hund's rule. This was the one that we explained sort of thinking about it in terms of a bus. If you get on a bus, you usually take an empty seat before you sit next to someone, right? So it's the same idea with our electrons. The electrons generally will take empty orbitals or empty seats before they start pairing up. So this only comes into play when you're filling in P, D, and F sublevels, where you have more than one orbital in the sublevel. But keep that in mind. Fill the empty seats first, then you go back and start pairing up once they don't have a choice. So if we look at question 3, it's asking, of those rules, are any violated in this particular orbital diagram? Okay? The question is, let's look at each of those in turn. So the Aufbau principle, are these orbitals filled from lowest to highest energy level? Yes, they are, because we started with 1s, then 2s, then 2p, so they did fill lowest to highest. So the Aufbau principle is good. So let's jot that off to the side here. Alright, so that one's good. Next up was the Pauli exclusion principle. So are the arrows all pointing in the correct directions? Do we always have one up and one down in a box? Still, yes, so that one's good too. The last one we need to check for is Hund's rule. So, did we fill up all the empty seats before they started pairing? And here's where we have our mistake, essentially. Okay? Right in here, rather than the way they filled here, the first box completely and then moving to the next one, that really should have looked like this. If I'm going to redraw this at the bottom, we should have that our 2p sublevel, if I fill in the electrons, there were 3 of them. So the first one should have gone here, the second one should have gone here, and the third one should have gone there. They all would have taken empty seats before they paired back up. Keep in mind, electrons are all negative, so they don't really want to be next to each other or close together if they don't have to. Okay? In a later video, or not later, in the video, excuse me, you did have to draw an orbital diagram, so I'll get to how we draw these orbital diagrams then if you're having some trouble. Okay? So, moving on to question 4. Questions 4, 5, 6, and 7 all deal with electronic structure. So this was sort of the stuff we talked about before we got to our formal electron configurations. Okay? So the first thing, what are the sublevels? The sublevels were designated with letters. All right? And those 4 letters were S, P, D, and F. All right? And when we drew our orbital diagrams and we talked about their structure, they all had a certain number of orbitals. S sublevels always have 1, so when we draw our orbital diagrams, that's why we always just drew 1 box for any S sublevel. P sublevels had 3, so we drew them like that. D sublevels had 5, so we drew them like this. And our F sublevels would have 7. 1, 2, 3, 6. Oop, 1 short. 7. There we go. All right. As for question 6, it asks how many electrons the maximum could fit in each of the sublevels. So if you look back to what we just drew over here in question 5, what we need to recognize is that each orbital, or each box essentially, can hold 2 electrons. All right, so if I basically take how many boxes there are and multiply that by 2, I'm going to get my answers to question 6. So an S sublevel can hold 2 electrons, a P sublevel can hold 6, D can hold 10, and F can hold 14, which those numbers are also not arbitrary. Remember, if we add the periodic table here, let me pull this up on the screen so we can see it. If we check out our periodic table here and bring that up for a sec. Notice that those numbers correspond with what we just had, right? So we said it was 2, 6, 10, and 14. Okay, so that's our solutions for question 6. So now if we move to question 7, it says how many electrons, so not orbitals, but how many electrons can each of the following energy levels hold? So the first thing we need to recognize is which sublevels are present in certain energy levels, right? So the first thing we're going to do is I'm going to pull up the periodic table again, because looking at the periodic table can help us figure out which sublevels are actually there. Okay? So the first energy level is easy to tell. The first energy level would correspond to the first row on the periodic table, and both of those we color-coded as S previously, meaning the first energy level only has S sublevels. So if it only has S sublevels, that means it has 2 orbitals, and it has 1 orbital, which means if we only have 1 orbital, 1 times 2 means we can hold 2 electrons maximum. Looking again at our periodic table, the second row of the periodic table, we see these 2 would be color-coded S, and if we continue our way across, these 6 are color-coded P. So the second energy level has both S and P. So we have the 1 orbital from the S, and the 3 from the P gives us 4 total orbitals, which would give us 4 times 2, 8 total electrons. Okay? Now the third row is where it gets tricky, because if we look at our periodic table, it looks like we should just have S and P, but if you remember the weird rule about this center section here, all of our transition metals there, we were labeling them as the D sublevels before, but we always wrote them as 1 row less than where they appear. So even though this section right here is actually in the 4th row, we basically take this whole piece and shift it up. So this would really be 3D. So if we went across this row, it would be 4S, 3D, and then 4P. Or think of it this way, every time you move down an energy level, you add a sublevel. So this one would have S, P, and D, meaning we would have 1 orbital from the S, 3 from the P again, 5 from D, so that would give us 9 total orbitals, which would be 18 total electrons. Okay. Last but not least, our 4th energy level, again, if we just add 1 more sublevel, would be S, P, D, and F. So that's 1 plus 3 plus 5, and then F was 7. So in total there, that would give us, 16 total orbitals. 16 times 2 would give us 32 total electrons. Okay. Now if you're curious about where that F sublevel is coming from, it really is right here, even though these 2 at the bottom here technically are in rows 6 and 7. The F sublevels we wrote as 2 rows less than where they were. So even though it's 6F, or excuse me, even though it's in the 6th row, we would write it as 4F. Okay? So that's how we would figure out how many electrons were in each of the energy levels maximum. Okay? Now in question 8, we're going into our electron configuration. So question 8, question 9, and question 10 are all kind of linked together with orbital diagrams, and these are the last 3 that'll be in this video. Okay? So first thing I want to remind you, let me grab that periodic table again. The first thing I want to remind you is that our electron configurations are always made up of 3 parts. We always have just as an example, I'll jot one down here, you always have a coefficient, a letter, and a number. Okay? The coefficient, so this one, always corresponds with the energy level on the periodic table. That corresponds to pretty much the row number. The letter corresponds to the sublevel, but on the periodic table it corresponds to sort of the section that we're at. So S, P, D, and then the bottom 2 rows would be F. And then the exponent here corresponds to how many electrons are in that particular sublevel. but on the periodic table it corresponds to kind of how many spots you're moving in that section. All right? When we are doing our electron configurations, remember we always, based on the Aufbau principle that we talked about in the beginning of this video, you always have to start with the lowest energy level and work your way up. So on the periodic table, that means we kind of do it like we read. We start at the left. You work your way across the entire row. Once you finish that one, then you start back at the left, work your way across that whole row, etc. So in other words, we're kind of filling in order of the atomic numbers. All right, so for this first one, if we are figuring out what the electron configuration for nitrogen would be, what we need to do is we would need to get all the way down to here, right? That's the 7th element, so we would need to fill in, essentially, elements 1 through 6 and include that 7th one as well. All right? So to fill our first section, the first thing I'm going to write would be 1s2. Okay? Writing that takes care of this one and this one. The 1 because we were in the first row, s because both of those were color-coded as s, and 2 because there were 2 electrons you're filling in. Okay, that row is done. Now we'd start back at the beginning of the second row. So starting the second row, the next thing I would write would be 2s2. 2 because we're now in the second row. S because we are still in the S color-coded section of the periodic table. And 2 because that would now take care of, those are already done, it would now take care of that one and that one as well. Okay, now our last piece is F still moving across the second row. Alright, so here's our second row, but now we're moving into the P sublevel. So if we're moving into the P sublevel, instead of writing 2s or something else, I'll now write 2p. But our exponent, while it could be a maximum of 6, because there are 6 total electrons right there, we only need to use 3 spots. 1, 2, 3 to get over to nitrogen. So our last piece would be 2p3. Okay, now how do you check your work here? We said, if you remember back in this unit, if you add all the exponents together, they should always equal the atomic number of the particular element. So nitrogen is the 7th element, so having 7 electrons makes perfect sense, because if it's neutral, we should have the same number of protons and electrons. Okay? Now, for the next example, for strontium, this one's going to be a little bit longer, because if you are thinking ahead a little bit, if we have to go through all of the earlier elements to get to the element we're writing electron configuration for, the lower the element, the longer the configuration will be. So, I'm just going to reset this for a moment. If you need to copy down the example for nitrogen, please make sure you pause the video right now and go ahead and copy that down while I rearrange this a moment. Alright, so we're now writing our electron configuration for strontium. Strontium is all the way down here. It's the 38th element. Okay, meaning this is going to be a little bit longer, but we'll start the same way. If you look, we'll see you'll have to fill the first row, the whole second row, the whole third, the whole fourth, and then part of the fifth. So I'm going to start off with 1s2, because that would take care of this one and this one. Then I'll have 2s2, just like before, because that would take care of those two. Now, we previously said 2p3, but we're actually going to need to fill this entire section, so that'll be 2p6. Now moving on to the third row. Those two, third row, S sublevel, 2 spots, so 3s2. And then to finish our third row, it'll be 3p6, because we're in the third energy level, the P sublevel where we arrange that, and 6 spots. Okay, moving to the fourth row. These two would be 4s2, and here's where it gets a little bit weird. Following our pattern, it should be, based on what we said already, 4d, because we're into the D sublevel now, we're still in the fourth row, and there's 10 spots there, so 4d, 10. However, we said the D and F sublevels are so large that they actually start overlapping their energy levels a little bit, so we write them as one row less than where they appear. So even though it looks like it should be 4d, we're actually going to write it as 3d10, and that takes care of all of these. Okay, so don't forget, D was always -1 from the row number. Okay, but now if we keep going, we're back over here, and these we were doing normally before, so we'll keep that the same. Fourth row, P sublevel, all 6 spots. So we'll move those across. So 4p6, and then to end us out, we're starting the fifth row. We'll do both of those spots, so 5s2. Okay, so a little bit longer, but this is the big thing that was different. Make sure you keep that in mind there. We didn't have any F electrons in this example, but the F sublevels, we always write them as 2 rows less. So if you had gotten down to like 6 or 7, you would have filled in those 2 and then moved down here, subtracted 2 from the row number, then back to here where we subtracted 1 from the row number, and then back to normal. But those are a little bit trickier. Okay, so there are full electron configurations. If you're writing a full electron configuration, you start with 1s1 and work your way up. In our next question, though, it asks about the abbreviated, the shorthand, or the noble gas configuration. They're all just different names for the same thing. So, how would we do these? Same process. Instead, though, of having to write all of the different electrons, what we can do is we can use a noble gas to represent some of the earlier electrons, and then we just have to fill in what's left, essentially. Okay? So if we look at calcium, if you find that on the periodic table, is right here. Okay? So what we did when we wrote our shorthand, we always looked to the row above the element we were writing the configuration for, and we looked for the noble gas. So if we go up and to the end of our row, we see that argon is the core. Argon has 18 protons, which means it also has 18 electrons. Calcium has 20. So basically you're picking the noble gas that is the closest in number to the electrons without going over. So the first thing I'll do is write AR in brackets. So we're using brackets there, not parentheses. But just writing that takes care of all the first 3 rows. So 1s2, 2s2, 2p6, 3s2, 3p6. So basically we already did all that. So all we need to do now is pick up where we left off. So if we pick up where we left off, that would be right here. So I only need to do these 2 spots. We're in the 4th row, the S sublevel, and we're moving 2 spots. All we need to do is argon 4s2. Much simpler than writing the full thing out, like I said. Okay. Now for gold, we're going to do the same process. Okay, but for gold, put that over there. For gold, it's a little bit farther down. So gold is down here. It's the 79th element. Okay, so again, same deal. Pick the noble gas in the row above it. So the noble gas in the row above it would be xenon. So we're going to write xenon in brackets. And now we write what's left. So just finished there. So picking up with the 6th row. First, I would do 6s2 to take care of these 2. Here's where those F sublevels come in, though, that I was just mentioning a moment ago. If you look at this one, every periodic table is a little bit different, but if you follow the atomic numbers, it goes 55, 56, and then 57 is down here. So the next section I would move into would be the F sublevels, but we said those we always write as 2 rows less. So even though these 2 technically fit right in here, and that one fits right there, we are going to write them as 2 rows less. So even though it should be in the 6th row, we're now going to write 4F. Now how many are there? On your periodic table, if you take a look, there should be 14 elements in that bottom section. So 4F14, that was the maximum number of electrons an F sublevel could hold. The periodic table I have on the screen is formatted slightly differently, so I would stick with the one that you have on your reference sheet. Now we need to keep going, so that would take care of all of these. And just cross them like that. So we now need to finish this section right here. So we're back to the D sublevel. We're still in the 6th row, but we said D's we wrote as 1 row less. So rather than writing 6D, we'll write 5D. And the question is just how many spots do you count over? If you count over, you'll see that there are 9 electrons in that particular section. Again, check out your periodic table, not the one I have on the screen. But that would be 5D9. So there's our shorthand for gold. Okay, again, much easier than having to write all 5 earlier rows and then this last part that I wrote there. Okay, so that's our shorthand. Our third way to write our electron configurations is drawing an orbital diagram or using what's sometimes called orbital configuration. Now I know we taught this a little bit differently when we did it before, so many of you in the review packet have been drawing them like this and so forth. You don't need to do that stair effect. Okay, it's perfectly fine. If you don't know what I'm talking about, that's fine too. What we're going to do is we're going to write the electron configuration and then just draw the orbital diagram underneath it, going from left to right across the page, just to make your life a little bit simpler. Okay, it said you can use the abbreviation if you prefer, so it's up to you whether you wanted to start with 1s2 and work your way up or use the shorthand. I'll do one of each. Okay, so if we start with phosphorus, follow along on your periodic table, but hopefully you feel all right making your electron configurations. So if you do that, the normal electron configuration for phosphorus would be 1s2 2s2, 2p6, 3s2, 3p3. Okay, so when we draw our orbital diagram, every part in this particular configuration needs something to represent it in the diagram. Okay, meaning I need something to represent this part, this term, this term, this term, and that term. All right, so what we drew boxes to represent the orbitals. Every s, let me write this off to the side here, every s sublevel will represent with 1 orbital. Every p sublevel we represented with 3. D's we represent with 5 because they can hold 10 electrons, and then last but not least, our F's would hold 7. 3, 4, 5, 6, 7. Okay, so if we draw our configuration for this one in particular, I see 1s2. So the first thing I'm going to draw is a single box, label it 1s, make sure you label them, and there are 2 electrons in there. The Pauli exclusion principle says that the first one has to point up, the second one has to point down. Okay? Next thing we see is 2s. So I'm going to, again, just draw a single box because it's an s, but I'm going to label it 2s so I know it's a little bit higher in energy. And those 2 electrons fill in like that. When we get to 2p, a p sublevel should have 3 orbitals, so I'm going to draw it like that and label it 2p. And all 6 of our electrons. There it's going to be completely filled, but it fills in a particular way. Based on Hund's rule, which again I mentioned in the first part of this video, the first electron always goes up, second one will go up and fill the second empty spot, the third one will fill that third empty spot. We take all the empty seats on the bus first before they go back up in pair. So there's 3, and then 4, 5, and 6 all pointing down. Then on to 3s and s, so we go back to a single box, 2 electrons in that, and then most importantly, looking at this last sublevel, the 3p sublevel is not completely filled this time. We only had 3 electrons, so how you fill them in is important. Keeping in mind Hund's rule, all 3 of those electrons are going to take all the empty seats first. They will not pair up yet. Okay, so that would be our full orbital notation, our full orbital diagram for phosphorus. Looking at this, you can see based on this part right here, there are 3 unpaired electrons in a phosphorus atom, which is why phosphorus generally forms charges of -3, because it will gain 3 extra electrons to fill those empty spots. Okay. Now for bromine, this one would be a little bit longer because bromine's a little bit farther down the periodic table. So for the notation, I'm going to use the shorthand. So again, you should be able to do this based on the examples we did before. But this would be our shorthand notation for our bromine atom. Okay, so if I'm going to draw this with our electron configurations, or excuse me, our orbital notation, I'm still going to make sure we put the argon in brackets, and now we just need to draw what's left. Okay, so if we're just drawing what's left at this point, I need something for the s, so 1 single box, but I'm going to label it 4s. Then we have a d sublevel, so I need 5 conjoined orbitals. And then a p sublevel would only have 3, and we label that. And then our electrons, we would fill in the 4s2 would go up and down. The d10, the first 5 would all go up. The last 5 would all go down. And then 4p5, again, Hund's rule. First 3 go up in separate boxes, 4, 5. So looking at this one, right here, we have only 1 unpaired electron, which is why bromine forms charges with an ion with a charge of -1, because they'll gain 1 extra electron to fill that empty spot. Okay, so there were plenty of other examples with electron configurations. If you need to look back in your old notes, look at old quizzes, we had quizzes from this unit, you'll have time with your test folders, etc. So make sure you're able to do this. Again, with the orbital configuration, I know a lot of you were writing them sort of in that stair effect. There's no need to write it like that. Perfectly fine just like this. Just write it left to right across your paper in a straight line. You know, if you run out of room, just start underneath it, just like you would with your electron configurations. Okay? So, those are all the questions from Unit 6. Excuse me, not Unit 6, Unit 9. Our next video will tackle the periodic table unit that we did, which was Unit 10. Alright? Thanks, guys.